Hello everybody and welcome to today's lesson on more factoring. Today our objective is we will be able to factor trinomials when a is not equal to 1. In our last class we started talking about factoring when a is equal to 1, so let's review quickly how we did that. First, we looked for a greatest common factor. Always remember to look for a greatest common factor first. We need to pull that greatest common factor out before we start factoring, or the rest won't work. Once we had a greatest common factor, or we had checked and there was none, we went ahead and found the target sum and the target product. And those we used to find our two numbers P and Q. And those are the ones we need for our factors. Once we had P and Q, we set up two sets of parentheses, and in those we put an X into each, and P and Q, and done. Today we'll talk about how to factor when A is not equal to 1. A, remember, is the coefficient of our squared term. When A is not equal to 1, we do everything the same until we get to the point where we fill out our parentheses. And what we do then is we plug in AX as opposed to X. Again, A is the coefficient of our square term. We plug in AX, so X with the coefficient. And then, though, we have to eliminate double counting. And I'll show you what I mean by looking at this example. 3x squared minus 17x plus 10. Let's find our target sum and target product first. Or before we even do that, do we have a greatest common factor? No, not in this example. Our target product is 30. Our target sum is negative 17. So which two numbers will give us 30 when we multiply them and negative 17 when we add them? Since the product is positive but the sum is negative, both numbers have to be negative. So let's do our little factor rainbow. 130, 215, 310, 4 doesn't work, 5 works, 5 times 6, and that's it. So both numbers need to be negative and they need to add up to negative 17. And with that being said, we see that the numbers we need are negative 2 and negative 15. All right, then let's set up our parentheses. We put 3x now into both of them, and negative 2 and negative 15. Now take a look at that. We have 3x in both parentheses, but we only had 3 as a coefficient once. So we need to eliminate it in one place, and where we eliminate it is where we can divide both terms by that number. 3x minus 2, there's nothing that they have in common, but 3x minus 15, we can divide both of them by 3, and then we get our final factors, 3x minus 2 times x minus 5. And we're done. So this is kind of like taking out the greatest common factor out of one of the parentheses, maybe sometimes even both. And the reason why we do it is because we used it twice in our first step. We can't do that, so we have to eliminate it again. And remember, you can always check your factors by foiling them, and when you do that, you should get back to the trinomial that you started with. Let's look at another example. 8x squared plus 10x minus 3. Is there a greatest common factor in these three terms? The answer is no, there isn't. So our target product is negative 24. Our target sum is 10. So let's see what our factors are. 1, 24, 2, 12, 3, 8, 4, and 6. So now what happened here? We have a negative product. That means one of the two numbers was negative, one of the two numbers was positive. The sum is still positive. that also means that the number with the greater absolute value had to be the positive one. So, for example, 4 and 6 won't work. They add up to 10, but they don't multiply to negative 24. One of the two numbers has to be negative, and the right pair here is negative 2 and 12. Okay, let's set up our parentheses. Put 8x into each of them, and then the negative 2 and a positive 12. And now let's see what we have here. We have 8x minus 2, and we can take out a 2 here, and we have 8x minus 12, and they have a 4 in common that we can divide out. So now our final two factors look like this. 4x minus 1 times 2x plus 3. And that is our final answer. If you want to be safe, go ahead and follow them, and you'll see that is your trinomial. And now you're pretty much ready to factor any trinomial that comes your way. But we will go ahead and take a quick look at special products, because for special products we can use a shortcut when we factor them and don't have to go through all the steps. Remember, special product is what we get when we take a binomial and multiply it by itself. So we have, in other words, a set of parentheses that we multiply by a set of parentheses with the same numbers inside. We have three different ones of these special products. The first two are called perfect square trinomials, and that's because they are created by getting a perfect square. A plus b squared, which is a plus b times a plus b, and the pattern of that is always a squared plus 2ab plus b squared. And the same if we have a minus b and we square it, a minus b times a minus b will always give us a trinomial in the shape of a squared minus 2ab plus b squared. And then there is the third one, and that's probably the most important one of all of them, the difference of perfect squares. The difference of perfect squares is something we get when we take a binomial and multiply it by another binomial that has the same numbers and variables in it, but one of them has a plus, one of them has a minus. If that happens, our middle term disappears, and all we're left with is a squared minus b squared. So, special products we recognize because they always have a perfect square in the first term and in the last term. That is true for all three of them. But then the perfect square trinomials, they have a middle term, and that middle term is twice the number of variable for A times the number of variable for B, and it has the same sign as the two factors. So if the two factors had a minus in them, then the middle term ends up with a negative sign. If the two factors had a plus in them, then the middle term ends up with a positive sign. And as always, let's look at some examples. X squared plus 6x plus 9. Is x squared a perfect square? Yes, it is. It's the perfect square of x. And 9 is also a perfect square. It's the square of 3. So this may be a perfect square trinomial, but for that, our middle term has to also work out. The middle term has to be 2 times the x times the 3. So 2 times x times 3, that's 6x. Okay, then we're good. We can set up our parentheses. This is indeed a perfect square trinomial. And in factored form, that's x plus 3 times x plus 3. Let's look at our next example. X squared minus 10x plus 25. X squared, we said, is the square of x. 25 is a perfect square. It's the square of 5. Now what about our 10x in the middle? Is it 2 times x times 5? Yes, that's 10x. But it's negative. So be careful with that. So our factored form is going to be x minus 5 from the negative sign times x minus 5. And there we have our two factored forms, way quicker than going through the normal process. And now let's look at our difference of perfect squares. X squared is the perfect square of x, and 81 is the square of 9. But we have no middle term. We have no middle term. The middle term gets cancelled out because the two parentheses, one of them had a plus and one of them had a minus. So we need to show that in a factored form, which then looks like this: x plus 9 times x minus 9. And we're done. Now realize that you could go ahead and factor all these three exactly the way that we factor any other trinomial, the normal way with finding our target sum in our target product, and then p and q, and we would get to the same answer. So when we see a special product, that's great, and we can use the shortcut. But if for some reason we don't see it, don't worry, just go ahead and factor the trinomial the regular way. Now the difference of perfect squares you will recognize because it looks different. It only has two terms, but even that one you could theoretically factor the normal way. The only thing you have to do is you have to realize that our target sum is 0. Now let's do this real quick. Target product is negative 81 and the target sum is 0. So what numbers would work for us here? 1 times 81, 2 doesn't work, 3 times 27, 4, 5, 6 don't work. We go all the way and until we get to 9, and 9 times itself. Since this number is a perfect square, it has one number that multiplies by itself to get it. And now how does this work? How can we get 0 with any of these pairs? The only way to get 0 as a target sum would be if we use a negative 9 and a positive 9. And that's what we have. X plus 9 times x minus 9. So again, realize you can always factor these trinomials the regular way, and recognizing special products is just a shortcut. And now we're ready to pull it all together into our checklist for factoring. And here it is. First step, we look for a greatest common factor. And again, this is something you always have to do. Always have to be sure to check for it. You may not always find one, but if there's a greatest common factor in there and you overlook it and start factoring, your target sum and target product are going to end up all wrong. So always look for a greatest common factor. The next step is look for a special product. Now that is really just a shortcut. If you find a special product, if you see it, you can go ahead and factor it using the shortcut. If you don't fret, because if you continue factoring the normal way, you will get to the same answer. And the normal way is right here, step 3. We find target sum and target product. Then, using those, we find our numbers p and q. And now we're ready to set up two parentheses. If a is equal to 1 in our trinomial, then we just put an x into each set of parentheses and p into one of them and q into the other, and we're done. If a was not equal to 1 in our trinomial, then we put that a times x into each of the parentheses, then add the p and the q, but then we have to eliminate our double counting. That's important. Don't forget that last step. We have to eliminate the double counting because we used a twice and we are only allowed to use it once. Alright, you guys. That's it for today, and I will see you in class.